Okay, so last week, if you recall, on Thursday, we had this wonderful quiz, and everybody in here has their quiz back now. But after the quiz, we started talking about limits, and that's going to be the first major topic of the course. So we're going to continue with that today, and I'll just briefly recall what we did. Since we have a limited amount of time today, no pun intended, sinking in, I'd love to see like the 10 seconds later the last one start. So we want to talk about one-sided versus two-sided limits. And if we have time, so I'm going to call it the algebra limits. That's what hopefully we can get through today. From here, once we get through today, then we're going to also start talking about computing some more difficult limits. Today we're going to stick with some pretty easy ones. And then later on in the week, we're going to talk about infinite limits. Right, so, well, we'll get to that later in the week. So let's recall that if we have a piecewise defined function, so for instance, I think last week we looked at something like this. Maybe it was a 4. Something like this. So if we have a piecewise defined function, we can get some funny things when it comes to limits. Okay, so we'll quickly graph this again. So we have a function which is defined as this nice parabola shifted up 1 when x is negative. At 0, you actually get the point 4. And once you go positive, you just get the line y equals x shifted up by 3. Right? And what we saw is that, well, if you move down this curve, it's approaching the value 1. Right? Doesn't actually hit the value 1, but it's approaching it. So we used the word target, right? And the metaphor was, okay, you're the general of an army and you're going to nuke some weapons factory, right? And you put down, there's my target. That's what I want to hit. Okay. Do you actually make sure that you hit that target? Well, you hope so, but right, you know those crazy missiles just go everywhere. Okay. And so what we feared, of course, is that we might hit an orphan. Or walking down the street, or maybe a whole orphanage, right? And we kill a whole bunch of orphans. But from the general's perspective, he did his job when he's targeted the weapons factory. Right? So, from our point of view, when we talk about limits, we don't care if we hit orphans or not. Okay? All we care about is targeting the weapons factory. Okay? And that's what the limit is. It's just where it's going. You don't actually care what it hits. So, some examples. Following. Well, let's say, let's go right here. When, say you're at -1. This function x squared plus 1 at -1 is going to approach the value 2. Turns out it will actually hit it. So, good job, guys. You didn't hit the orphans. So we can write down that as x goes to -1, our function targets the number 2. Okay? It happens to hit it there, but that's completely incidental. Okay? We only care about what it's targeting. Yeah?
Would that be 3?
Well, let's see. When you put in 1 squared plus 1 is 2. So 1 plus 1 is 2, just so we're all on the same page. It's okay. Okay, and one thing that I'm hiding under the rug here is I came down this maybe from the left side and looked at it, but I also could have come up the right side and looked at where it was going. Okay, but it doesn't matter, right? This one, it hits the same place. So we just write this expression. But as we get closer to 0, then what side we're coming in does matter, right? If we target from the left or target from the right, you're getting different targets. Yeah. Okay, so for instance, maybe there's two generals now. One is a good left winger, and the other's a right winger. Okay, and the left winger says, well, we should be, targeting, one factory, and the right winger says we should be targeting another factory. Okay, so that's the situation we have. So let's see if we look. As x approaches 0, the left winger says we should be targeting what? 1. And remember, the way we denote that we're coming from the left is we take the number that x is approaching and put a superscript, either a minus if it's coming from the left, or a plus if it's coming from the right. Okay, now if it's coming from the right, what is the function targeting? Targeting 3. Very good. Now, if the two generals, one from the left, one from the right, can't agree on what they're going to target, well, then you can't give the order, right? You can't say, okay, we're targeting this factor. So, the order for targeting at 0 does not exist. If the limit from the left does not equal the limit from the right, then the limit without any reference to left or right does not exist. The same thing would be true if one of these didn't exist, even, and the other did, then of course they're certainly not targeting the same thing. Okay. So, if the two generals agree, you can, then you get a limit. All right. If they don't agree, you don't get a limit. Okay, fine. Now, these here are what you're not going to be surprised know are called one-sided limits. And I think the motivation for calling them such is obvious. This one here is a two-sided limit. And what we've just discussed is that a two-sided limit exists if and only if both one-sided limits exist and they are the same. Okay. Any questions? Pretty straightforward, right? Okay, so let's do an example where we don't have a graph. An easy one. What is the limit? Call that example A. The limit as x goes to 2 of x squared minus x plus 1. You can use words. 3? Okay. How do you get 3? Okay, you plug the 2 in. Okay, now if you plug the 2 in, this will come out to be 3. Okay, no problem. Right? Turns out to be the correct answer. But what doesn't sound right about just plugging the 2 in?
Because
Anybody? Yeah?
Usually you have to manipulate the equation somehow because, I don't know, like if it was like a fraction, you'd have to cancel.
Okay, so you're using pre-knowledge.
Oh yeah.
So without using pre-knowledge, what did I say? Is the point about these limits?
that it's not what you target, like the target. You're looking for your target, not for the exact number.
Exactly. All right. When I write this, it does not mean, at least a priori, that I can just plug it in and see what I get. Okay. I really have to see what happens near 2. I have to say, okay, very close to 2, what's happening, right, on the left and the right. And if they agree, right, then boom, I can write down this 3. Now, it's going to turn out that a lot of functions you can just plug in the value. Those are really nice functions. And we're going to give those a name. So this does things a little bit out of order from the way textbooks like to do it, but I think now is the perfect time, given our metaphor. War. So, if you were not only a good general, but you were really good at getting your people to do what you told them to do, and you had really good equipment, then when you said, target this weapons factory, where's that missile going to hit? It's going to hit the target, it's going to hit the weapons factory. It's not going to kill the orphans. All right? So those are the kind of functions we want to deal with. Ones where they don't just have a limit, right? They didn't just targeted something, they should hit their target. So when mathematicians talk about nice functions, that's what they're talking about. They're talking about functions which hit their target. So I give you a little definition. It's going to come in 2 parts. Then we'll come back and do more examples. So part A. Well, for part A, let's say let f of x be a function okay, assume I have some real number a, which is in the domain of f. So this is, it makes sense now. F of a is it's some value. Okay? It's not dividing by 0. It's really in the domain. I'm not sure if I use this notation yet. The domain of f. So if A is in the domain of F, then we say that F is continuous at A if the limit as x goes to A of f of x is equal to f of x. Which in words, if f hits its target at A. Does this, in principle, make sense? What I'm saying, you have some function, and you say, okay, at this point, I have a target. You always have a target of the function, right? Fine. Does it hit the target? If it does, it's continuous at that point. If it doesn't, it's not continuous. We call it discontinuous. Okay, well, I could have a really nice function, which is continuous at every single point. Right? So no matter where you go, it's always going to hit its target. Right? And those are almost the best functions we're going to talk about. Not quite the best functions, but almost the best. They're going to be called continuous functions. So if f is continuous, at every point A in its domain, then we call f continuous. Right? Or we say is a continuous function. So our first approximation of what a really good function looks like is a continuous function. So let's look at this piecewise defined function. Where is it continuous and where is it discontinuous? Well, it's continuous whenever it hits its target. So tell me, is it hitting its target all along here?
Mm-hmm.
Absolutely. Where's the first place it doesn't hit its target?
One.
At 0. Okay. So k of x is continuous on, so we'll say is continuous on some set. Okay, so it goes from minus infinity to 0, and it is continuous, but at 0 it doesn't hit its target. Right? So it's not continuous at 0. Okay? Because it, it hops up here, right? And then it comes down. And now, as you go past 0, is it hitting its target all the time? Absolutely. So it's also continuous from 0 to infinity. So, if you like, this is the set of all real numbers except for 0. So it's almost continuous, although I shouldn't use that phrase because mathematicians have a very specific meaning for almost continuous. And that's really horrible, isn't it? Well, it almost hits its target some of the time. That sort of deal. Okay. What about this function here? X squared minus x plus 1. You think that's going to be a continuous function? Sure, right? You never have any weird problems with a square. It's just a nice parabola. Right? And of course, it always hits its target. So this is a continuous function. Okay. Now, if you look back here at this definition, and of course we said it's continuous if f hits its target at the point. Okay? But what does that mean mathematically? It means that if you take the limit, you get the same thing as you expected if you just plugged it in. So continuity basically says you can plug in the value. You don't have to worry about this as a limit. You just plug in the value. Now, this is a nice polynomial. And if you ever, look at the graph of any polynomial, what do you know about it? It's just some nice smooth function, right? Never have any weird hop arounds or anything. You'll notice this continuity problem is accompanied by this big jump. And this is a specific kind of discontinuity called a jump discontinuity. It jumps up. But polynomials never have that problem. All right, anywhere, right? At every point, they're okay. Which means that polynomials are always continuous functions. So whenever you have the limit of a polynomial, boom, you just plug in whatever x value you're approaching. So I already said at the beginning, you never, ever plug in the value, right? Because you don't care about what happens at that point. But as soon as you know it's a continuous function, then you can forget that rule and just plug in the value. So generally, all polynomials are continuous. Okay. Let's look at another example. Let's look at the limit as x goes to 0 of 1 over x. What's the target? 1 over x. 0? Does 1 over x approach 0? Okay, so let's say you take some small number like a half. 1 over a half is 2. Put in a third, a fourth, a fifth, what do you get? 1 over a fifth is 5, 1 over a tenth is 10. So as you approach 0, it's actually getting bigger, right? And if I put in 1 over a trillion into this, then I get 1 over a trillion, which is a trillion. And so what's happening to this thing? It's going up to infinity, right? It's getting as big as possible. So, am I right to put down infinity? Why not? What's that? Well, 1 over infinity doesn't make sense, because infinity isn't a number. Right? So you can't write 1 over infinity. Okay? But certainly as you get closer to 0, you take smaller positive numbers, right? This thing does blow up. I mean, look at the graph. All right, what's happening to 1 over x as you get close to 0? Just does that, right? So, it wouldn't be so wrong to say that it goes to infinity, right? The target is infinity. But what am I not checking? The other side. Right? I've only checked the right side. So what I can write is this expression, but with a plus on the 0. Okay? So as I approach 0 from this side, well, the only reasonable thing to say is that it's going up to infinity. So this is the first example of an infinite limit, right? Which is something we'll talk about more. What if I went from the other side? You guys hear that? We have a suggestion that it's negative infinity. Does that make sense? Let's see. Well, if you put in small negative numbers, like minus a half, right? Well, then you get 1 over minus a half, which is minus 2. If you put in 1 over minus 1 over 10, you get negative 10. And if you put in negative 1 over a trillion, then you get negative a trillion. And of course, if you graph this thing, which is a hyperbola, it just goes down like that. So from the left side, the target is negative infinity. Okay, so what is then the limit as x goes to 0 of 1 over x? Everybody can say this at once. Does not exist, right? I have two one-sided limits, and they're not the same. It does not exist. All right. Now, what if I went anywhere else but 0? If I go anywhere else but 0, are the limits always going to exist? Right? Am I always going to hit the target?
No.
No. Who believes no? Okay. Where am I going to have a problem?
Infinite?
Well, infinity is not a number.
Well, everywhere, right? 'Cause if you try to take the limit of -2, it doesn't approach it from the right. Well,
Let's see. So -2. Right? So this should be negative a half. Well, as I approach from the left, it goes to minus a half. And as I approach from the right, it goes to minus a half.
you don't do it for the top half, right? Or
Okay, so this is a good question, right? Let's say I start approaching it, but I don't approach it from so close. Right? Maybe I start approaching it from over here. Is that what you're...
yes, that's what I was thinking.
Okay, that's an excellent question. What's the answer? Well, the answer is, when we talk about limits, we don't really care about what happens to the function far away from the point. We only care what happens to the function really close to the point. Now that's not a very good definition because I didn't tell you what the heck it means to be close to the point. You know, sometimes close might be within 1, sometimes it might be a half, sometimes it might be very, very small. Right? To answer it correctly, that's where we would have to use all this rigor about epsilons and deltas and all the... There's a very formal definition which gives a precise meaning to very close, right, which we're not going to give. But suffice to say, we only care about what I would call a neighborhood of this point. So I just go a little bit to the left and a little bit to the right, and look what happens. Now, again, you have to be careful what you mean by a little bit, because that's not precise. In math, you have to be very precise. When I say a little bit, what does that mean, a little bit? You know, it's kind of like my wife will say, I bought a shirt today. And I said, oh, really? How much was it? Well, it was pretty cheap. What do I have to do? I have to ask the same question again. Okay, how much was it? A little cheap? I don't know what you mean by a little cheap, right? Okay, the same thing here. I'm going to say, okay, I'm a little bit away. Okay, just for now, it just means you can make it as close as you want. And you're only looking very, very close. Right? You're kind of zooming in on it as much as possible. Just seeing what it's doing near that point. So, but that is an excellent observation, right? When I'm approaching it, I'm not approaching it from arbitrarily far away. I'm just approaching it from very close. Okay, so let's get back to this question of what happens on this function if we're not looking at the limit as we approach 0. Does the limit always exist? And is it always equal to the actual evaluation of that function? Right? Any ideas? And does anybody have another observation that says, okay, it's still not going to exist everywhere? Yes?
It's never going to cross the horizontal axis either. I don't know how to say it, but...
That's true, right? It won't ever cross the horizontal axis. Does that cause a problem when it comes to the limit? So you might be thinking, but okay, if it's getting close to the horizontal axis, then it must be targeting the horizontal axis, right? And it never gets there. So that's a problem, right? No. Why isn't it a problem? Well, what do we target? Do we target the axis? Right? Are we targeting some point like that? Or, if we look back at the definition of continuity, right? Are we targeting the function at a specific point? Right? We're always targeting at a specific point. So, it's okay that in the long run it never hits the x-axis down here. Because all we ever care is that at some point, does it hit the target at that point? Okay, so if I pick -2, my target is -0.5, and yes, it sure does hit it. And so it turns out that, yes, absolutely, at any point other than 0, it will hit its target. And so it's continuous everywhere away from 0. So like this function, it'll be continuous on the set of real numbers that are not 0. And in general, if you have any function divided by another function where the top and bottom are both continuous functions, then it will, the quotient will be continuous except when you get a 0 on the bottom. And so next time we'll write that up more precisely.